Good afternoon. Welcome to this afternoon's research results presentation hosted by the ODOT Office of Research and the LTAP Center, the Local Technical Assistance Program. This is Victoria Beal, and we are going to be hearing today about the evaluation of driveway assistance devices in signalized work zones. Your main presenter will be Deborah McAvoy, but she also had co-researchers Bhavin Naik and Jean Hartline. So if you have questions for the presenter, she will be stopping periodically to take those. There is a question box in your GoToWebinar panel, and I would ask that you find that now and just drop me a hi or hello so I know that you know where it's at. But that's how you'll also send questions in during the presentation. We are attempting to record the presentation. As long as that goes successfully, you'll be receiving a link to the recording after the presentation is complete. So with that, I'm going to turn things over to Dr. McAvoy.
Good afternoon, everyone. I hope you're enjoying your first day of spring on Monday. We are going to go through this presentation. The driveway assisted devices, you will hear me frequently refer to them as DADs. So just a shortened, abbreviated version. I think that's the only thing that you should be aware of before we start. I want to go ahead and thank a few folks before we get really started. First of all, ODOT and the Federal Highway Administration for obviously sponsoring this project. But we would really specifically like to thank ODOT District 5, Doug Morgan, RJ Starkey, and Austin Ditto for helping us through setting up the project, getting on their roadway, State Route 60, coordinating with the contractor, and being able to collect the data along the roadway, as well as further guidance and their assistance throughout the entire project. And also like to thank Shelley and Sands for allowing us to be on their work zone site for the collection of that data. And our last thank you goes out to the ODOT Central Office, both Jill and Patrick, for their advice and guidance as we have moved through the project. Just a quick outline of what we're going to go through today. We have some little bit of background on the DAD devices, what the project is really entailing, what the project looked like for State Route 60. We did a field survey, collected data out in the field, so we will talk about that in full, and then we'll move on to a household and contractor survey that we conducted, complete that. We did a microsimulation study because not everything is obviously available to be collected in the field, so we simulated some of that data. We will talk about that in full and then move on to a sensitivity analysis, trying to understand if conditions in the roadway were to change, what would happen to the data collection that would be seen in the roadway. And then we will move into the last section, which is benefit to cost analysis, and talk about some recommendations, and then we'll get to questions at the end if you haven't gotten a chance to ask those up to that point. So moving on to the background, we have a lot of roadways across the nation that are two-lane, two-way roadways. And in order to construct those roadways, we generally have to do that part with construction. So shut down a single lane, utilize the temporary traffic signal devices on the ends of the work zones in order to alternate traffic flow northbound and southbound or eastbound and westbound, depending upon the configuration of the roadway. But along those rural roadways, there are random driveways strewn throughout, and every once in a while you'll end up with a low volume roadway, and sometimes even commercial driveways such as a gas station or a restaurant. And being able to control those driveways by allowing traffic flow, we have to also put some type of traffic control device there in order to maintain those 24-hour operations. And when we use those traffic signals at those driveways, that really incurs a lot of delay along the mainline roadway, which causes queue buildup at the end of the roadway in order to be able to provide individual access and control points for those driveways along that rural roadway. And so the idea is that these DAD devices would try to alleviate those delays and tried to accommodate a little bit better traffic flow along that main line. So the DAD devices, as you see here, this is just an example of one of them. They do operate with a red arrow, and they give them a flashing arrow and allow them to be able to turn into that direction. They can join an existing queue of vehicles. They don't have to wait for a full signal phase for them. They could, and we'll talk about what compliance of that signal would look like here in a little bit, but it has the capability of improving that workflow, improving safety, because the last thing that we would want to see along a one-lane roadway is a head-on crash. But the problem that is that they're not fully approved by the Federal Highway for inclusion into the MUTCD, which is why this study was undertaken, was really to try to add to the portfolio of research that has been done already on the DAD devices. So the portfolio really goes all the way back to about 2009. Texas DOT, these are just pictures of a variety of the DAD devices as they have gone through their growth pattern since 2009. Every single one of the studies has essentially shown promising results in terms of the traffic operational performance. There have been some levels of driver confusion. That has really changed the way that the DAD devices have been configured. And we're really trying to hone in on what is the best configuration. ODOT had a different configuration in 2021. The 2022 studies where we utilized the new configuration. And so really trying to understand, with this new configuration, have we honed in on a DAD device configuration that is understandable by the public and also improves the traffic flow along the roadway system. So our objectives for this project were really to evaluate the performance of both the temporary traffic signal devices as well as the DAD devices at driveways. We want to look at the driveway traffic and are they complying with the device, either the temporary traffic signal or the DAD device? What are the operational impacts? So the delay, the queue on the main line, as well as the delay in the queue along the driveway traffic itself. Are there safety conditions that have arisen because of the use of either one of these driveways for the main line and or the driveway? And are they cost effective? And so that goes into the benefit cost analysis that we have done. And then last objective was to provide recommendations on when these devices should be utilized and how they should be implemented. So our project, like I said at the start, consisted of 4 distinct phases. And instead of just bouncing back and forth to talk about the data analysis, data collection, and then results, I have combined this into, we're going to talk about the field studies wholly, and then we will move on down the line, and then we will have a summary at the end so that you don't have to get confused as to all the various pieces of the project. So for the field study, we did use State Route 60 in Muskingum County. It is a rural arterial, and there's a picture of it for you to kind of get an idea of what it looks like throughout the entire project length. ADTs, pretty low, 3,800 vehicles per day, 13% heavy vehicles as it is a state route. They were doing a full depth pavement and replacement, a little bit of widening, and the work zones were approximately 1,000 feet in length as they were moving along the roadway to reconstruct the roadway. We utilized MyoVision cameras at all the driveways as well as at the end of the 2 work zones in order to capture all the traffic operational and or safety and compliance at the driveways and along the main road. We have 432 observational hours, which is 24 hours of data for 2 separate weeks, one in summer and one in the fall. And we will talk about the 2 different types of work zones that we were looking at. So work zone 1 and work zone 2 were collected simultaneously. Or work zone 1 and work zone 3, I'm sorry, were collected simultaneously. Work zone 1 included DAD devices. Work zone 3 was a little bit further up the roadway, and that's where we utilized temporary traffic signal devices. And then the second round of data collection was work zone 2 and work zone 4, and they were both DAD devices. We did end up having one temporary traffic signal in work zone 2 because we had a low volume roadway, and it was thought best at that point to go ahead and utilize the temporary traffic signal to control traffic. But every other driveway was controlled by the DAD device in work zone 2 and work zone 4. You can see on the table that we had a variety of configurations for the driveways. The vast majority of those configurations were a single family home. We did have one driveway in each condition. For the DAD device, it was a church in work zone 1, where you can see it is, use my laser pointer here, maybe. Work zone, the 1 church is right there with the larger parking lot. And in work zone 3, which would have been the temporary traffic signal device, was a construction business. And so other than that, all the driveways were very essentially similar, single family homes, but we did have that one more populated and utilized driveway in each of those conditions, the DAD device and the temporary traffic signal device. In terms of the data that we collected a lot of data, and you can see just an example of what the data collection videos looked like. They're not very high quality, as they're just screen grabs, but we were able to identify the direction of travel for both the main line and the driveway, which helped us identify whether the driveway vehicles were being compliant or not with that signal control device at the driveway. Looking at the platoon on the mainline vehicles, looking at the speed of that platoon, trying to figure out when the vehicles and the queue arrived at the driveway, when the vehicles departed the driveway in relationship to that queue. How long was the queue at the driveway? How long was the queue at the end of the work zones? Were there any conflicts between the main line and the driveway vehicles? And really looking more a lot of that turn compliance. And so when we talk about that turn compliance, I have a few diagrams here that I think depict what we were looking at and how we were describing how those vehicles leaving the driveway were compliant and whether or not they were safe. So some other research programs have utilized these same categories. And so the first category we were considering is compliant and safe. And so in compliant and safe, the driveway vehicle has their yellow turn arrow. And in this case, they were able to turn right. And so they turned right and they entered the flow of traffic well with beyond 150 feet of the nearest vehicle. So they complied with the device and they were safe in doing so because they were away from the vehicle that was on the main line. We also have non-compliant and safe. So there is a time where vehicles could have a red arrow, which means they're not allowed to turn. However, the drive or the mainline traffic was well beyond 150 feet from them when they made that turn. So they did not comply with the device, but they did so in a very safe manner to avoid a collision. We also had a scenario where they could have also not complied with the device, but they did turn within 150 feet of an oncoming vehicle. And so that could have resulted in an angle crash or a side swipe crash. So that is why it was deemed non-compliant and unsafe. And then the last condition is if they were to not comply with the device and turn into the direction of traffic flow on the main road. So that is completely unsafe, which would have resulted in a head-on collision. And so that is how we have categorized those 4 levels of compliance. And then I said we collected a lot of data, so this is just a real summary. I don't expect you to read this, but it gives you an idea of all the information that we were able to collect, the direction of their travel, their turn direction, the mainline direction of travel, how long they were waiting, how long was the queue length in the driveway, And then we were able to determine their compliance as well based upon all this information. And so we took that information and we were able to go ahead and summarize that. And when we look at the driveway waiting time, and so that is the delay of the vehicles that were in the driveway waiting to make a turn. So for the DAD devices, that turned out to be about 48 seconds, whereas the temporary traffic signal device folks, they were waiting about almost 90 seconds. So that was a fair amount of substantial delay that they were experiencing with the temporary traffic signal devices. Excuse me. The driveway queue lengths, as you can see, are very, very similar. 1.14 for the DAD devices, 1.08 for the temporary traffic control devices. I will say the vast majority of these driveways were single-family homes. So during the peak hour, you would not expect a lot of driveway traffic at these intersections of these driveways. So the queue length seems very reasonable for what we were witnessing. The mainline travel speed was a little bit slower because of the DAD devices. And I'm going to talk about a rationale as to why we feel that that was happening here in a little bit, but it's about 5 miles an hour slower. In terms of the mainline queue length, so this is at the end of the work zones that were both controlled by temporary traffic signal devices. The queue length was about 5 vehicles for the DAD devices and about 7 for the temporary traffic signal devices. And you can see our sample sizes, even with 432 hours of data collection over 24 hours, sample sizes were fairly low. Again, a residential area, not a lot of traffic, and a rural area as well. So we would not expect a substantial number of sample sizes in this area. Obviously, we would have loved to have been larger, but given what we have on the situation with the rural roadway, it's fair and reasonable. In terms of their compliance summary, the DAD devices experienced a 80% full compliance, whereas the temporary traffic signal devices were just above 20%. When we look at, whether they were non-compliant and safe, the temporary traffic signal devices were still safe maneuvers at 30%, 31%. So overall, the temporary traffic signal devices weren't wholly unsafe. Just a little bit more than 50% of the time they were operating in a safe fashion. But you start to look at the non-compliant and unsafe, 30% for the temporary traffic signal devices is an unacceptable range. That just leads us to the potential for crashes. And then about 19% traveling in the wrong direction for the temporary traffic signals, and about 12% of those for the DAD devices. Now, trying to understand what was happening at these devices, we broke these down a little bit further into, at the end of the work zones, for both conditions, we had driveways where the motorist could see the end of the work zone traffic signal, and they could tell whether it was green or red. And when it turned red, they knew that the traffic would be getting green from the opposite end of the roadway. And so we really wanted to see if because they could see the end of the line traffic signal, was that impacting their judgment in their decision making to violate the traffic signals. And you can see for the DAD devices, it really wasn't that much different, 80 to 82.6. However, the temporary traffic signal devices was much higher. And so because they could see those end of the work zone signals, they were making decisions because of that. And that goes back to the fact that there was a substantial increase in the wait time at the driveways because of the temporary traffic signal devices that were controlling the driveway. And it ends up those folks got a little bit impatient and they started to make improper procedures and really trying to jump the gun there. And so that is really the big takeaway from the compliance data. In terms of the operational analysis, I just have the overview over here on the side, but driveway waiting time, the dads had shorter waiting times. The dads had slower speeds, and the dads had shorter queue lengths on the main line as well. The queue length, as we talked about on the driveways, there was no significant difference there, 1.08 to 1.14, so we wouldn't expect a difference. We didn't see a difference. But all the other three parameters were statistically significant. Now, I did want to talk about this travel speed because I said it was different, and the dads did yield a slower speed. And sorry for the coughing. And one of the things that we can notice is because of the ability for the vehicles to make a maneuver, it seemed that the mainline traffic was aware that the driveway folks would be more than likely turning, and they were traversing a little bit slower because of that. And then on the other end, the traditional signals, they had substantial queues at the end of the main line, and a little bit of frustration. We saw some compliance issues at the end of the work zones for the temporary signals, jumping the gun, impatience, and so that is probably replicated as well in that speed within the work zone. Now, in terms of, how much time are they really different? And so the dads did end up yielding about 0.3 minutes shorter waiting times at the driveways. The dads yielded, we were able to detect up to about 2.5 mile an hour slower speeds based upon the analysis. And we were able to detect about a 1.22 vehicle shorter queue length. And so that detectable difference is, we have a practical difference and a statistical difference. And so this is the practical difference. That yes, it was statistically significantly different, but it was also practically different. And we can tell you exactly how practically different they were. And so that is helpful in order to, when we move that back into the benefit to cost analysis area. So looking at our compliance analysis, we have our temporary traffic signals and what number of vehicles were compliant with those. Based upon those percentage, we were able to create a expected rate, just equivalent percentages of what the dads should have yielded. And then we see what the dads actually did happen in the field, and that is what the dad's device observed column is for. And so now we get to compare through the chi-square test whether the 35 and 124 are similar or different, and indeed they are very different. So we can say that the DAS devices have substantially higher compliancy than the temporary traffic signal devices at driveway control. So overall on the field study, the DADs have shorter delays, they have shorter queue lengths along the main line at the end of the work zone, and they have much higher levels of compliance. Now, before we really get into the survey questionnaire, I just want to go ahead and see if anybody had any questions regarding the field study before we move on.
There's one question. It says, is the high number of unsafe traffic signal violations at driveways or on the multi-lanes?
We only had one lane open on the main line and one lane on the driveway. So there were no multi-lanes. This was just a single lane work zone.
That's all the questions right now.
Okay. We'll move on to the survey questionnaire. The aim for the survey was really to understand, do the drivers, can they comprehend the traffic signal, the DAD device signal, and also to find out the construction folks. the folks that are out there on a daily basis, how do they feel about the operation of this signal? So as you could expect, we had low response rates for both the household and the construction personnel. But in general, most of the folks were able to understand and comprehend the DADS device at a pretty high rate. And the construction personnel, they all preferred the DADS. None of this was real quantitative. We tried to get a productivity rate to be able to compare the construction and the temporary traffic signals and with the DADS, and they were actually equitable for this particular case. But in general, the construction folks felt that the excessive queues at the end of the work zone were impacting the delay of their vehicles arriving to the site. They felt that then was improving or impacting their productivity on the site. Most of them felt that they had improved safety with the DADS. And they preferred utilizing the DADS on a daily basis as opposed to anything else. Now, because we didn't have very high rates, we just left this as some qualitative data that kind of correlated with everything else that we found in this study. All right, moving on to the microsimulation portion. So for the microsimulation, what we ended up doing is we had work zone 1 and work zone 3, and we ended up having them both with work zone 1 with the temporary traffic signals and work zone 1 with the DADS, work zone 3 with the temporary traffic signals, and work zone 3 with the DADS, so that we had a comparative parallel analysis that we could conduct. And we kept it with work zone 3 and work zone 1 because they each had one driveway that had higher levels of vehicular traffic, as opposed to work zone 2 and work zone 4, which only had these single family homes. So we were able to simulate those work zones. We did make a few changes. We replicated the mainline traffic, but because we only generally saw an average of one vehicle at the driveways, we went and upgraded that and added 4 vehicles per hour on the driveways to see if that would really, as our baseline, to see if that would make a difference. Because one vehicle was leading to very low data collection, which replicated what we saw in the field. We used a 15-minute warm-up period and a 60-minute simulation period. And for each of those 4 scenarios, ran 30 simulation runs. In terms of the operational data that we collected, control delay, just like we did in the field for the end of the work zone, as well as the driveways, the travel time along the main line, and then the queue length for both the end of the work zone as well as the driveways. In terms of the analysis, you can see that 4 vehicles per hour on each driveway really impacted the temporary traffic signal devices. So the waiting time in seconds was 23 seconds versus the DADS was only 1.77 seconds. And so the DADS did yield shorter waiting times for the driveways. And in terms of queue lengths, the temporary traffic signals also had a larger queue length of 0.5 feet versus DADS of 0.14 feet. So the DADS did yield statistically significantly shorter queues as well. So both of those elements mimicking what we saw in the field. And then looking at specifically just work zone 1, and I will talk about why we're doing this here in a few moments. Looking at the travel time for northbound and southbound, DADS yield shorter travel times. The queue delay for northbound and southbound at the end of the work zone, the DADS also yielded shorter queue delays. And when you look at these are substantial. In terms of the queue delay at the end of the work zone, 11 seconds versus 7 seconds, 17 seconds versus 5 seconds. And so the DADS were certainly making improvement along the end of the work zone. The queue lengths are also substantially different. So 300 feet of a queue length northbound, 238 southbound for both the temporary traffic signal devices, When we talk about the dads, it's 117 versus 66. And so there's a substantial difference in the queue lengths as well, which correlates directly to the delay. And so the dads do yield shorter queue lengths. In terms of the queue stops, so this is where we have a different finding. So the temporary traffic signals left fewer queuing stops. And that simply could be because of the operation, the way that the vehicles are moving through the DADs. They're more consistently stopping and going. So that is somewhat explained as well. But the queue stops, I don't think is nearly as important as both the queue length and the queue delay. Those are very important, particularly for the end of the work zone situations. When we look at work zone number 3, we end up with some mixed results. And we also end up with some similar results. So the travel time results end up being very, very similar to work zone 1. So the DADs do yield shorter travel times. In terms of their queue lengths, the relationships are also very similar. 218 queue delay for northbound, 414 for southbound. For the temporary traffic signals, we only have 21 seconds for the DADs and 26 seconds for the DADs. So statistically significantly shorter queue delays. Now the queue lengths are a little bit different. 212, 347. And so we start to see, that was a mystery. These are exactly the same. The signals have larger queue lengths, so the DADs do have smaller queue lengths. Where we see the different results is in the number of queue stops. So again, the queue stops, we have shorter for the signals, longer for the signals. And so those are some mixed results that are a little bit different. And I do want to go back and look at, to show you is work zone 3 versus work zone 1. And so when we look at work zone 1, we have essentially a very straight alignment along the roadway. There's a slight curvature toward the end, but work zone 3 does have a curvature along the entire length of the roadway, which we're hypothesizing that is what is causing the change between the results that we are seeing. And so looking at installing a work zone along a curve is something that we might want to consider moving forward. All right, I will stop right there and ask if anyone has any questions on the VISSIM simulation portion.
There's no questions on this portion.
Okay. Then we will look at the safety simulation using the FHWA surrogate safety assessment model. And we did not see, there were no reported crashes along the work zones during our analysis period, or actually during really any time this past year. So we want to be able to try to predict crashes by looking at conflict data. And the conflict data that we like to look at is time to collision or the post-encroachment time. For those of you that don't know what post-encroachment time, it's the time one vehicle leaves and another vehicle arrives. And the shorter that gets, the shorter that gap is, there's a higher level of conflict that could occur for that intersection. So because we don't have crashes along the roadway, this is a great surrogate measure in order to find out, are there safety problems through these work zones given these two different types of devices? So when we look at work zone 1, we have the fact that the DADs have longer time to collision time frames. So it is safer in work zone 1. Work zone 3, traditional devices end up with a higher time to collision. And again, it's going back to that potential of that geometric alignment that could be causing sight distance issues, ability to see down the roadway, ability to see past a queue, ability to see upcoming driveways, which causes the DAD devices to drop in terms of safety. We look at the post-encroachment times, we see very similar results. The DADs yield a longer post-encroachment time, therefore DADs are safer in this circumstance. And again, work zone 3, the temporary traffic signal devices have a longer post-encroachment time, meaning that temporary traffic signals are safer for controlling driveways in work zone 3. So we're starting to see a theme on that straight alignment versus curved alignment issue. When we look at the crossing and the rear end conflicts that are potential for both the temporary traffic signal and the DAD devices, for work zone 1, very consistent. The DADs do yield fewer crossing conflicts and the DADs yield fewer rear end conflicts. The DADs do yield fewer rear end conflicts when we are talking about work zone 3. However, it is those crossing conflicts where we start to see the issues for work zone 3. And so the traditional temporary traffic signals do yield fewer crossing conflicts. And again, it goes back to sight distance and the ability to see oncoming traffic and the ability to make judgment calls as you're at the driveway, and being able to, have the folks that are utilizing the DADs being able to make judgment calls whether to join a queue or not. So the temporary traffic signals do provide improvement there, but again, only potentially because of the geometric alignment that is affiliated with work zone number 3. We were able to validate the results with the field study. So when we ran the microsimulation, we compared it to the field study. We were able to validate. We found very similar results. And we can say that the DADs yield shorter delays, shorter queue lengths at the driveways, shorter delays, shorter queue lengths at the main line, shorter travel times through the work zones, higher level of driver compliance. And then when we get to work zone number 1 versus work zone number 3, with that curved alignment, that is where we really start to see the differences in the safety alignment. So that curvature needs to be looked at a little bit further, but for straight line roadways, work zone number 1 was a much safer scenario. All right, before we move on to the sensitivity analysis, does anybody have any questions on the microsimulation safety aspect?
None that have been submitted so far.
All right, you guys are holding all your questions till the end. All right, for the sensitivity analysis, we wanted to look at and say, all right, well, what happens if the mainline traffic volume substantially changes? And what happens if the driveway volume substantially changes? So growing the mainline volume from 300 vehicles per hour up to 3,500 vehicles per hour, and growing all the driveway volumes from 4 vehicles per hour to 100 vehicles per hour, and trying to understand what are those impacts. And looking at just the driveways here for a second, we have the driveway input for 1030 going across here. And these are their delays for each individual driveway that was looked at. What's important to note is everything is really generally below 50 seconds of delay, with the exception of one of the driveways. And then after 50 vehicles per hour, delay really becomes unacceptable in terms of greater than 50 seconds. So we have a level of service F for almost every single one of the driveways. And this becomes a little bit more unstable. When we look at the queue length, we see the queue length corresponds right to that 30 to 50 vehicles per hour. Is after that, things start to get very unstable and excessive queue lengths at the driveways. Also looking at the driveways in terms of their safety, So we have our time to collision that is in blue, our post-encroachment time that is in yellow. And obviously, the fewer vehicles that you have along the driveways, the higher levels of time to collision and post-encroachment time you will have. And as you start to increase driveway volumes, your post-encroachment times will then start to decrease. Things seem to stabilize right between 30 and 50 vehicles per hour on the driveways. The conflicts, there's no lane change conflict because it's only one lane. And the conflicts do substantially increase. But I think the time to collision and the post-encroachment time is the piece to kind of hone in on and say there seems to be a stabilization, again, honing in on that 30 to 50 vehicles per hour. Looking along the main line for delay for northbound and southbound is on the top. Queue length is on the bottom. Plus 30% point on each one of these graphs relates to about 5,000 ADT on the mainline roadway for each direction. And you can see that once we get to about that 30%, it does stabilize. There is some substantial growth as you get up to that 5,000 vehicles for the queue length and the delay. But as you expect, this really turns out to be almost an excessive amount of queue length for both northbound as well as southbound traffic volumes. So we really just wanted to focus in on what happens with work zone number 1 because of the geometric alignment issues with work zone number 3. So we focused in on work zone number 1. The DADs do yield less than 50 seconds of vehicles per delay when we're dealing with 30 to 50 vehicles per hour along the driveway. They end up with a stable time to collision and post-encroachment time at about 50 vehicles per hour. Mainline traffic volumes up to 5,000 vehicles per day leads you with 14 vehicles in a queue at the end of the work zone. And then longer all red signal timings. We also changed the all signal timings. They did not increase the delays at the queue for the driveways. So the idea is you can increase the all red time for the driveways without substantially impacting their levels of service. All right, any questions on the sensitivity analysis?
No questions on this section.
Okay. All right, looking at the benefit to cost analysis, we looked at, considered engineering design and planning cost, work zone traffic control cost, maintenance cost, road user costs that are affiliated with travel time, delay, and crashes, and then the noise cost. We ended up throwing out the engineering design and planning cost because we assumed that the planning and the design pieces that are affiliated with the temporary traffic signals, as well as for designing the signal timing plan, would be similar for either one of the scenarios using the temporary traffic signals or the DADS devices. So that was not considered. We did, however, did consider the work zone traffic control devices and the maintenance of both. We did consider all road user cost. We did not consider the noise cost. Both of the work zone devices require generators. Both of the household groups that we surveyed did comment on the noise of the generators for both the temporary traffic signals as well as the DAD devices. So we assumed that those were similar moving forward. And like I said before, we were not able to find a difference in contractor productivity for either of these projects. So that was not considered in the benefit to cost analysis either. In terms of the work zone traffic control devices, the temporary traffic signals cost about $5,600 per month, and the DADs cost about $1,800 per month. So those were the fixed fees at the beginning. The maintenance of the traffic control devices, because the DAS devices and the temporary traffic signals both require generators and solar panels to assure that 24-hour operation, we assume that the cost would be similar with a few caveats. Some of the dads ended up with solar panels that were located at the bottom of the trailer. That led to loss of power after 6 weeks. And so they required an additional generator at a cost of $500 every 6 weeks and an additional maintenance of 6 services, about $250 a service. So those were factored in, and we utilized those to understand what happens if we have to use the DAD devices that have the solar panels at the bottom of the trailer, as opposed to mounted above the signal head. Looking at the road user cost parameters, these were pulled directly from either the simulation and or the field study, looking at the driveway delay, the travel speeds, the queue delay, the queue lengths, the queue stops. We were able to determine a passenger vehicle value of time based upon the average salary earned in the Muskingum area along State Route 60, and then multiply by a factor to determine the truck value of time. But they are similar for both circumstances, so if those change, everything will change with that. And then a passenger vehicle running cost, the cost of $1 per mile, and a truck running cost, $1 per mile. Looking at the roadway parameters themselves, we assumed 10 driveways for each device, 4 vehicles per driveway. We said everything was about a mile in length, 1,000-foot work area, and being able to understand how much of the road was at running speed and how much of the road was at the slower speed, knowing that there's a 55-mile-an-hour speed limit, and then we have the work zone speeds themselves. So there we were able to determine the cost of travel time because of the differential in the work zone speed traveling through either the temporary traffic signal device or the DAD device. Looking at cost parameters, really looked at the National Safety Council, and we were able to talk through the idea of a property damage only vehicle would be a non-compliant, unsafe maneuver with greater than 3 seconds of the time to collision. Injury type C will be affiliated with an unsafe maneuver less than 35 miles an hour, non-compliant, unsafe, less than 3 seconds. Injury type B, somewhere between 35 and 45, and a fatal collision would be if there was a head-on collision greater than 45 miles an hour. They looked at the number of crossing conflicts and the number of rear-end conflicts that the simulation provided to us for each of the work zones. And we were able to go ahead and total those and summarize those for the temporary traffic signal devices and for the DAD devices. And you can see, as everybody that does benefit cost analysis ratio, once you include conflict cost ends up being the vast majority of the cost affiliated with the project. So we ran this a couple of ways with the total road user cost, and then we subtracted out the conflict cost, knowing that that can skew the results substantially. And so we end up with a road user cost savings without the conflict cost of $655,000 for the DAD devices. Their cost minus their benefits, their total cost. If we just consider the cost itself, it's a benefit to cost ratio for the DAD devices of 7.6. If we utilize the road user cost savings without the conflict cost, it ends up being a 153.37 to 1. So the DAD devices are obviously very cost efficient. All right, questions on the benefit to cost analysis?
Yes, we've got one.
Awesome. Okay.
It says, going back to the mainline volumes, did you say 5,000 VPH was similar with DADs as the temp signal, or is that the threshold when signals might be better? And I can read it again if you want.
Yep.
Going back to the mainline volumes,
Yep.
did you say 5,000 VPH was similar with DADs as the temp signal, or is that the threshold when signals might be better?
We did not compare those to, we were just looking at, in that situation, what happens when we increase traffic along the main line to 5,000 vehicles per day. The signals, regardless, based upon the previous simulation, the signals would produce a much higher level of Q than the DAD devices, regardless of what is happening on the main line. So the traffic signals will have, if you have 14 vehicles of Q utilizing the DADs with 5,000 vehicles per day, you would have substantially more with the temporary traffic signals. Which is what the field study.
Sorry, this is the only question you've got right now.
Okay, all right.
He said thank you.
Awesome. All right, so some of the research gaps that we have: sample size, obviously, we have 18 continuous days of data, single family homes, left us with 155 and 211 sample size, which is adequate for a study. Geometric alignments should be further evaluated based upon that work zone number 3 that we looked at through the simulation. And commercial driveways with more than 30 to 50 vehicles per hour should clearly be evaluated as well. We only had one on each. They did not rise to the level of 30 vehicles per hour, but those should be evaluated a little bit more carefully moving forward. So when should DADs be utilized? All driveways with less than 30 to 50 vehicles per hour can keep levels of service below 50 seconds of delay. Mainline volumes, 5,000 vehicles per day, will yield about 14 vehicle queue lengths. Signal phasing can be designed for the highway capacity software to optimize that traffic flow. The geometrics need to be considered for curved roadways. The DADs, to improve the benefit cost analysis ratio much higher than the 153, go ahead and use the solar panels that are mounted above the signal heads. And there should be some advanced notification to the homeowners because of the potential noise associated with any type of driveway control device, to get them a little bit on your side to understand how long is this situation going to be in effect, how loud is it really going to be, and what are areas that they can do to help mitigate those situations within their home. In terms of the expected benefits and cost, all the road user costs, the queue cost, the crash cost are more costly than equipment and maintenance. And when we only consider the equipment and maintenance, DADs are still the most economical solution. And then again, to maximize those, use the DADs with the signal heads above those solar panels above the signal heads. In terms of the risks are proportional to driver compliance. The DADs is significantly higher in compliance than the temporary traffic signals. So any safety risk that is going to happen with the DADs will be substantially higher with the temporary traffic signal devices. There's no way that you can really negate any risk. It's a work zone, there will be risk, but the DADs certainly does minimize that risk altogether. All right, with that, hopefully you folks will have some more questions that have come up. Now that you've been pulled in.
I'll say there's no more currently in the question box, but we can give them a second or two to go ahead and type them in. Yeah. Or if someone really doesn't want to type them in, there's few enough people on here that I'm fine. If somebody wants to raise their hand, I'll be happy to unmute them and then they can ask the question. Okay, I was looking to see, I thought I saw somebody raise their hand. Raise it again. Oh, must have been a mistake. Oh, wait a minute. Actually, Raphael has his hand raised. Let me go ahead and unmute him. And it says you are self-muted as well, Raphael, so you'll have to unmute yourself on your end. There you go.
There you go. All right. I think you were saying that you can handle 30 vehicles per hour in a driveway. Did y'all look at how to handle that many cars with a DAD, since a DAD only lets them go in one direction at a time? Like if the first car is going left, but the next car wants to go right and the next car wants to go left, did y'all look at how to accommodate that?
So we did, and we ran through a variety of
Raphael, if you can mute yourself, thanks.
all right, so we ran through the simulation where we did randomize those directions, and because of the way that you can time the signals, you do not have to give as much time to each individual driveway as you do with the temporary traffic signal devices. It provides much higher response rates to be able to provide that appropriate time for the vehicles that are turning right or left. And usually when you end up with 30 to 50 vehicles turning right or left, similar to the church parking lot that we had, when people were trying to leave, it was one lane going right and one lane going left, so they were queuing up in separate lanes. So that was also factored in.
Okay, that makes sense. Y'all having separate lanes, just those.
Yep.
Thank you.
Okay, I haven't seen any additional questions come in the question box, and I'm searching to make sure no one else has got their hand raised. Nope, I don't see anybody else, so. All right, going once, twice. All right, we'll let you go ahead and wrap it up then.
All right, well, thank you guys all for your time today. I do appreciate it. If you have any questions, you're welcome to reach out. And you will be, I believe the final report will be available through ODOT.
It will. It'll be on the Office of Research's website. And as I'd mentioned at the beginning, we did attempt to record this presentation. So if we're successful, you'll get a link to the recording as well as a link to the presentation. Thank you, everyone. Have a good rest of your day.